All right. So let's move on to 5.5. We're going to talk about double angle identities in 5.5, and we'll also talk about sum to product and product to sum identities here. So just to bring us back up to speed, what we've talked about so far are all of these fundamental identities, from the co-function identities all the way down to the double angle identities here. Or sorry, the Pythagorean identities. We're going to talk about the double angle identities today. Okay, so these are the ones that we're going to talk about. But in the first, I guess 5.2, 5.3, did we start in 5.2? I can't remember. But we've talked about these ones as well. So we've talked about all of these, we've talked about these, and today we're going to talk about double angle identities, and then also kind of briefly product to sum and sum to product identities as well. So let's get to it. Okay, so double angle identity for cosine. These just come from the sum identities for sine and cosine. So cosine 2a turns out to be cosine squared a minus sine squared a. And we can prove this by saying, well, cosine 2a is just cosine of a plus a. And then you apply that sum formula, right? Cosine a plus a is cosine a minus sine a. And sure enough, right, you get cosine squared minus sine squared. We can think of different ways to formulate that, right? Because we know that cosine squared is just 1 minus sine squared. So another way to say this is 1 minus 2 sine squared a. We also know that sine squared is 1 minus cosine squared. So we could also call this 2 cosine squared minus 1. Okay. Now, I'm not going to prove the rest of these double angle identities, but they're similar, right? Just if you want to prove that sine 2 theta is 2 sine theta cosine theta, just call 2 theta theta plus theta and then apply the sum identity, and you'll get there, right? Same thing with the tangent 2 theta business. As for the product to sum, so this is a product, cosine A times cosine B, and you can turn that into a sum where you're looking at cosine of A plus B and cosine of A minus B instead, and this is the formula that does it. Generally, like here are all of the product to sum identities. Okay, and to prove this, we actually work backwards. So we start with the right hand side, and we can apply a sum formula, right? Cosine of A plus B is just cosine A cosine B minus sine A sine B. Cosine of A minus B is the same thing, but the sign in the middle changes. And then you combine like terms and you get cosine A times cosine B out of that. All right? So, and again, I'm not going to prove the rest of these, but they're all similar. Okay? Let's practice applying these, though. So we'll work out several examples. So I've got, oh goodness, 1, 2, 3, 4, 5, 6, 7, 8, 9 examples to show you of applying these kinds of formulas. So so let's do it. So given cosine theta equals negative 12/13 and sine theta greater than 0, let's find sine 2 theta. Okay, well, sine 2 theta is just 2 sine theta cosine theta. That's the double angle identity for sine. So in order to find this, we need to know sine theta and we need to know cosine theta. Well, we know that cosine theta is negative 12/13. So we could use either a Pythagorean identity, or we could just draw a right triangle and solve for the missing side or whatever in order to find sine theta. You might recognize at this point that this 12/13 thing is part of a 5, 12, 13 triangle. okay? Which means that sine theta is going to be 5/13. And since sine is positive, it's going to be positive 5/13. But, you know, if that's too quick for you, you know, draw the triangle. Cosine is negative, but sine is positive. That puts you in quadrant 2. Right, 13, negative 12. Solve for the missing side. I promise you're going to get 5. Okay? And then you can see that sine is 5/13. Okay? But anyway, so you get 2 times 5/13 times negative 12/13. And the rest is history, right? 5 times 12 is what? 60. 60 times 2 is 120. So this is negative 120 over 169, I believe. Okay. So there's sine 2 theta. Let's do cosine 2 theta. Go ahead and pause the video, see if you can work that one out on your own. Okay, a couple ways that I can think of to go about this. I mean, for one thing, you already know what sine 2 theta is, so you could draw a little right triangle and just find cosine 2 theta from there, potentially. There might be some ambiguity as to what quadrant 2 theta is in, and so that could affect the sign of cosine 2 theta. So maybe you have you know, some issues with that, but I think you could probably do it that way. But I'm just going to apply the identity, right? Especially since we were given cosine theta. So I'm going to use the version of this identity for cosine 2 theta that only uses cosine theta. That way I don't have to find anything else. Of course, I've already found sine theta, right? So I guess it wouldn't be too much of an issue to do one of the other two. But I like this middle one because it only uses the information I was given. And so that means that there's less room for human error. So cosine 2 theta, I'm going to call 2 cosine squared theta minus 1. And so that's going to be 2 times negative 12/13 squared minus 1. Negative 12/13 squared is 144 over 169. 2 times that, I guess, would be 288. And 1 is 169 over 169. So let's see, 288 minus 169 is 119. So this is going to be 119 over 169. That's interesting. So theta is over here in quadrant 2. 2 theta must be in quadrant 4. It seems that that's the case because cosine 2 theta is positive. Okay, and then we can do tangent 2 theta. Well, I mean, that's kind of silly, right? You already know sine 2 theta and cosine 2 theta. Tangent 2 theta is not too difficult from there. If you wanted to use this double angle identity, you could do that though, right? You've already solved the right triangle, so you know that tangent is negative 5/12. Okay, so then you can just say, you know, tangent 2 theta is going to be 2 times negative 5/12 over 1 minus negative 5/12 squared, right? So you could use that, but I'm just going to use the easier identity, right? I know that tangent 2 theta is sine 2 theta over cosine 2 theta, and I've already found those values in parts A and B, so that's cosine 2 theta is 119 over 169, but I'm going to flip and multiply. Instead of dividing, I'm just going to go ahead and flip and multiply. And there you go. And that's that. Okay, so that's that first set of examples. Here's another one. So let's find the 6 trig function values of theta given that cosine of 2 theta is 3/4 and theta is in quadrant 3. Ooh, okay. Give the video a pause, see if you can figure that one out. Okay, here's my solution. I think I'm going to actually use this identity again, because I can use this identity to find what cosine of theta is. And then if I know cosine theta, I can make the little right triangle, and I can find all the other 5 trig functions from there. So I'm going to say cosine 2 theta equals 2 cosine squared theta minus 1. Well, that implies that 3/4 equals 2 cosine squared theta minus 1, since cosine 2 theta is 3/4. And then I can solve for cosine theta. If I add 1, 1 is 4/4, so if I add 1 I get 7/4, right? And then if I divide by 2, you get 7/8 equals cosine squared theta. And then if I take the square root, cosine theta is plus or minus square root of 7/8. Now, theta is in quadrant 3. And in quadrant 3, cosine is negative. So I'm going to take the negative square root. In fact, if I split this, I have root 7 over root 8. Square root of 8 is just 2 root 2. And then if I well, I don't know. I don't want to get too carried away trying to rationalize this stuff. But if you rationalize it, you could multiply by root 2 over root 2. You'd get root 14 over root 2 times root 2 is 2, and 2 times 2 is 4. So that would be the rationalized version of cosine theta. And then you can find the other 6 trig functions from there. I'll be honest. I've been recording a lot of lectures today. And I'm not sure I'm gonna finish this problem, because finding the other 6 trig functions is easy at this point, right? You make your little right triangle, solve for the missing side, and then you can get sine, tangent, cotangent, etc. So I'm going to leave it there. Okay, let's look at another one. So let's see if we can use this information to verify some identities. I should have left more space for myself maybe. But let's see if we can verify that cotangent x times sine of 2x equals 1 plus cosine of 2x. Let's see if we can verify that. Give the video a pause, see if you can do it. Okay, so here I go. My inclination is probably to start with the left-hand side. I mean, I don't know. The left-hand side, right-hand side, they both seem kind of equally complicated, but I'm going to go ahead and rewrite sine 2x as 2 sine x cosine x. And in fact, then I can change cotangent into cosine over sine. And maybe, well, it doesn't matter. I'm going to simplify here in a second, because then I can cancel off a sine. And that's just going to give me 2 times cosine squared x. Okay. Well, that's not looking like the right-hand side yet, but if I start on the right-hand side, maybe I can meet in the middle. Right? So 1 plus cosine 2x is 1 plus, well, I want to get this to just be something in terms of cosine alone, so I'm going to use my favorite little identity, 2 cosine squared x minus 1. Right? Oh, and then sure enough, the 1's cancel, right? And you're left with 2 cosine squared x. So I guess the logic flow would go in this direction. You'd start here, and then go there, and then go there, and then from here you would go to here, and then there, and then there. Okay? But that does it. That proves it. Okay? So we've proven it. Let's do another one. So let's verify this one. All right. So see if you can verify that cosine 2x minus sine 2x squared, quantity squared, is 1 minus sine 4x. So I'll let you work. Okay, here I go. Now I could be wrong about this, but I have a feeling that I'm going to have to expand what's on the left-hand side in order to verify this identity. That's where I'm just going to go ahead and start. Okay. You FOIL it, right? You can't just distribute the exponent. You should know that because you're coming into this class from college algebra, right? So you can't just distribute the exponent, you have to FOIL it. And this is what you get when you FOIL that out. I notice that, okay, this thing here in the middle, this is maybe a little bit difficult to see at first glance, but notice that this is like 2 sine something times cosine some of the same thing, right? It's 2 sine something times cosine of that same thing. Well, that's just a double angle identity for sine. This is just sine of double this angle. It would be sine of 4x, right? This thing is just sine of 4x. Oh, and that does it, right? Because then also notice when you put cosine squared and sine squared together, you just get 1, right? Okay, so check it out. We've got cosine squared 2x plus sine squared 2x minus 2 sine 2x cosine 2x. This thing is 1. This thing is 2 sine of double the angle, right? 2 times 2x, which is just 4x. It's 1 minus 2 sine 4x. Okay, so there you go. Alright, a couple more examples. Actually, I think I have 3 more examples in total, but let's try this out. Let's write each function as a trig function of x alone. Okay, let's see if we can do this for cosine of 3x. Ah, that's interesting. Well, I'll let you give the video a pause and see if you can try it out. Okay, so here I go. I think I'm going to have to use a sum formula here. I think I'm going to have to treat this like cosine of x plus 2x. And then I can apply the sum formula, right? Cosine a plus b is cosine a cosine b minus sine a sine b. Okay? Now I still haven't quite done it because I want these things to be trig functions of x, not trig functions of 2x, right? So I need to use now, I need to use a double angle identity on both of these things to get rid of them. Now which version of the double angle identity you use here, I don't know. I don't think it really matters. So I'm just going to call it cosine x. I'm just going to stick with my favorite, right? So I'm going to call it 2 cosine squared x minus 1. And sine 2x I can call times 2 sine x cosine x. Okay, and then you're done, right? That's it. You know, now that I'm looking at it, here I'm going to get 2 sine squared cosine. If I had used the sine squared version of this, I could get something similar and probably simplify it. So I'm going to actually use this one, 1 minus 2 sine squared x. Just because I think I can do a little more simplifying that way. We'll see. So I'm going to get cosine x minus 2 cosine x sine squared x minus 2 sine squared x cosine x. I'm just going to rewrite it so it looks the same as the one I just did. Yeah, because then I can combine those like terms and call it 4, right? Cosine x minus 4 cosine x sine squared x. Okay, well, it wasn't an identity that they wanted us to verify, so I don't know what the end goal is supposed to look like, but that one looks pretty good, I think. Okay, and we've done what we set out to do, right? We've written these as trig functions of x alone. Okay. In fact, we could get all of these in terms of cosine. Use a Pythagorean identity here, call it 1 minus cosine squared, which is maybe what I would have gotten if I had just stuck with my guns up there. But anyway, okay, here we go. Here's another one. Let's do this for cosine 4x. Okay, you probably know the trick. Give the video a pause, see if you can do it. Here I go. I'm going to do that. Okay. So then I'm going to have cosine 2x minus sine 2x sine 2x. Oh, this one's really nice, I think. Okay, because then I get cosine squared 2x minus sine squared 2x. And now check it out. When you have a cosine squared of something minus sine squared of that same thing, well, that's just cosine of 2 times the thing, right? That's exactly what I've got going on here. Cosine squared of 2x minus sine squared of 2x. That should just be cosine of 2 times the thing, the argument, right? That's just cosine 4x. Oh, but then I've gone backwards, right? I don't want to do that. Oh, that's silly. That's silly. Look at me going in a loop. How ridiculous. You're probably all looking at the screen like, what is this guy talking about? Okay, so maybe I don't want to do this then. Maybe what I want to do, actually, is use double angle identities. So I'm going to call this 2 cosine squared x minus 1 times 2 cosine squared x minus 1 minus, oh goodness, 2 sine x cosine x quantity squared. Okay, there we go. So I suppose you could FOIL this out now. I don't know how far we want to really take this, but we could call this 4 cosine to the 4th x minus 4 cosine squared x plus 1, and then minus 4 sine squared x cosine squared x. Okay, that would be acceptable, because now we've rewritten all of the functions in terms of x alone. Alright, well, one more. This is kind of a silly one too, but I think you'll have some problems like this in the homework. So let's simplify 2 tangent 15 degrees over 1 minus tangent squared of 15 degrees. Okay, give it a pause, see if you can work that out. Okay, here I go. Hopefully you noticed that's just exactly the double angle identity for tangent, right? So this is just 2 tangent, or sorry, not 2 tangent, it's This is just tangent of 2 times 15 degrees. That's tangent of 30 degrees. I never remember tangent off the top of my head. It's sine over cosine. Sine 30 degrees is 1/2. So this is 1/2 over root 3 over 2. So 1 over root 3, or if you like, you could call it root 3 over 3. Okay, there's that one. And that will do it for 5.5.